Alright, everyone, I'm sorry in advance for this day. This is something I'm not really too happy with, but let's just go ahead and get started. Alright, so I'm actually going to go ahead and try this out, see how this looks. Alright, so if I go ahead first, we get a grid like this. I'm going to go ahead and do my favorite, complex numbers. So we'll also create a class for this. So we'll have our init, and so we'll just take in our input, just so we'll process it all in here. I'll go ahead and just create this class here. So g is equal to grid on input. So now in this actual input, let's go ahead and save a couple things. Let's save the size of our grid, which is going to be the len input.splitlines. And then our grid itself will be a set. And the reason why it's a set is because we're only storing basically if it's a wall or not. So we just need to see if it's in there or not. And self.positions is also going to be a set, because this is basically going to be the set of all the positions we're at. You can see basically every time we take a step, we like kind of step out a position like this. And so I just want to be storing these. And also the nice little property is now a set won't store a duplicate, so I won't have to worry about that. So now that we have that, for y, l, and enumerate, all dots input.splitlines, for xv and enumerate l. And now we'll go ahead and actually just process our input. So we'll do if v is equal to the hash, then self.grid.add point at xy. If v is equal to the start symbol, self.positions.add p xy. So now if I go ahead and just, I'll print out these. So print self.grid, self.positions, and then if I run this, we can see you're basically getting some outputs, no errors, so that's good enough for me. All right, let's keep going. So now we're reading our position. Now let's write a function to do a step, like how we do here. So step, it's going to take into self, and then now we'll just calculate all of our new positions. So for p in self.positions, and then for direction in each of the 4 cardinal directions, nice little property of complex numbers again, and then we'll do if not p plus d in grid. So if the position we're trying to move to is not in the grid, meaning it's not a square, then that's a valid thing. So, I'm sorry, this is supposed to be if p plus d not in grid. Oops, alright, okay. So now, with this, what we'll do is, that'll probably go away. We'll add this to our new positions. Alright, so now that we have that, let's go ahead and actually save our self.positions is equal to new positions. And now if I do g.step and I print out g.positions, we should see these 2 squares here. Let's see where we're getting. Grid is not defined, that's my bad. Self.grid. Alright, so here you can see we're basically, we start off in 5, 5, and we have 1 that's 1 above it, 4j, and then 1 is the left fit. So that looks good. And if I go ahead and just do this one more time, we can see we get 4 positions. 1 is 3, 5 here. We have 5, 3 here. We have 4, 6 for this one. And then 5, 5 at our starting space. Cool, so this works. And so now if I go ahead and actually print out here, print g.size, print g.positions, and I'll get rid of these. And if I run this on my actual input, you'll notice that our size is 131, and also I'm only storing one size because the input is a square. It looks like that's consistent, but also we are starting at 65. These 2 numbers will matter, so let's pay attention to it. But let's go ahead and do part 1. So for this in range 64, and we'll do s for step. And we'll do g.step. Now we'll do here p1 g dot, we'll do len of g dot positions, and let's do none. So if I run this, you can see we're getting the right answer here. So basically we're just counting how many different unique positions we have after this step. Notice how I also didn't really worry about this going out of bounds, because if you look, we start off at square 65, and this is 131. 65 times 2 is 130, meaning basically I could take 64 steps and I will not hit the edge of my grid. That's just a little property of the inputs, so I don't need to worry about like this going out of bounds with the grid, anything like that. And then we get to part 2. We have an infinite grid. So, to implement that, at least just naive in our code, we'll go ahead and write a function called wrap self p. And so what this will do is basically just wrap it around. So to do this, I'll do return a new point where p.real is mod by self.size and p.image is mod by self.size. So basically this is just going to wrap around. So if I, for example, was at all the way at the left here, and then I go 1 to the left here, it'll give me basically self.size minus 1. So it'll wrap it around. And same for all the other coordinates. So because of this, now, if I want to see if it's touching the grid in any square, I'll just do self.wrap p plus d. And so now, if I go ahead and I do this, let's say 66 times, and I'll print out g.positions, we'll see here, we'll see a couple things that are like out of bounds. So I would expect to see maybe like -1 somewhere. So if I control F for -1, you can see we're getting like a -1j. So it's now going out of bounds and it's working as intended. So here's the part where I'm so sorry in advance. What the smart people on Reddit figured out, and I sure as hell didn't, if you look at your input, so this is your S, this is your start position. Notice how there's no, if I select this line, for example, there's no walls on this line. And if I look at the vertical line, I don't know how to select it. You can see there's also no walls like that. Interesting little property. And so, basically, if I take 65 steps, I will basically fill out one square with all the possible things I could reach in one kind of iteration. And then, if I did an extra 131 steps, I will basically, 131 steps is how much it takes for this point to go all the way in one direction and then wrap around to the other side and come all the way back and hit this again. And so it ends up kind of, in a weird way, looping. Except here, if I basically draw it like this, I have one square here. Maybe it's better if I draw on this. So if I have one square here, let me choose a nice color. There. So I have one square like this. When I start at the beginning and I do my 65 steps, basically enough to fill out one of these and start touching the other direction, that's basically me filling out a square, something like that. And then when I do 131 steps, that's the same as me reaching out here, 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 and here, because 131 is the length of this kind of square. And so now if I continue and do another 65 steps after doing 131 steps, that's the same as me basically filling out this entire region. And if you notice, we go from one square, then we do 131 steps, and then we get 5 squares. And if I do another 131 steps, each one of these branches out, and so forth. And so we start with this, then we add on 4 more. Then from this, we add on 1, 2, 3, 4, 5, 6, 7, 8, 8 more. So we have 1 plus 4 plus 8 plus, and then it kind of keeps going. If we add this on one more time, I think we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I feel like I messed that up. But we end up with something like this. And if you can somehow figure this out, this ends up being a quadratic pattern. I'm going to be honest, my brain's a little bit fried right now, so I'm not seeing it too much, but I feel like if you added up these numbers itself, you kind of start seeing a pattern. But yeah, so basically from that, people figured out if you look at 65 steps in, which is the time it takes to fill up like one square, and then you check it 65 plus 131, you would see some linear relation. And then if you checked it again at 65 plus 131 plus another 131, you would see another relation. And then after that, it kind of caps out because this pattern is kind of quadratic. So they just fit it into calculators. So if I go ahead and basically take this, and I'll do 64, here, we'll go ahead and This is going to get ugly, so bear with me. So I'm going to basically store a list of my x points, my y points, and they create a function where basically it's like f of x is equal to how many squares are visited at time 65 plus 131 times x. This is our f of x that we're kind of fitting here. So we have all of this, and then now we also have, we need to get like all three values from this. So the way we'll do this is we'll do 65 plus 131 times 2. So this is basically f of 2, and then plus 1 because we have ranges, and the range isn't inclusive, so we'll add 1 here. So now, at least for part 1, we'll do if s is equal to 64, then we'll do part 1 is equal to len g dot positions, like this. And then here we'll change this to p1. Alright, and so just a little sanity check. Actually before I do it, let me just go ahead and keep writing this. So we'll do now if s mod 131 is equal to 65, so if it's one of my f values, so first I'll run at 65, then 65 plus 131, so forth. I want to add this to my, whatever my value is, I want to add this to my y list. So we now have this, and then if I go ahead here and I print out x, y, let's see what we get. How about I don't have any extra prints? Yeah. And we're going to put some magic here. This is going to take roughly 20 seconds. You can optimize this code. I tried a couple different optimizations, and it did make it faster, but just in the interest of keeping this code simple, I didn't do that. But the cost of that is my code takes around 20 seconds for this. But if we see here now, at 0, we're getting 3791, 33646, 93223. Wow, what a coincidence. These are the values I already have in this calculator. So when we try to fit this polynomial, we end up with this formula. And so if I go ahead and now take this formula, and the x value that I'm solving for will be target is equal to the value they give us, which is this. And again, smarter people than me figured out, oh look, if you subtract 65 and divide by 131, you get a nice round integer. And I can show that if I copy this value, and it doesn't copy because I'm using thin keylines, but here, 131, we get a nice soft round integer. If I now plug this into Wolfram Alpha, the equation we get, would you look at that? This value, if I copy this, and if I Control F, that's my answer. So proof by it works for my solution, and it works for other people's solution. But yeah, so go ahead, and the part that I'm going to hate myself for is I want my code to just run and output the answer. I don't want it to actually have to go into Wolfram Alpha and manually do it. So what I found out is there's a cool little library called NumPy. So if I import NumPy, what I can do is use the function np.polynomial.polyfit on x, y with a degree of 2. So I'll save this to poly for now, and if I print this out, and this is going to take another 20 seconds. Oh, cool. Oh, import numpy as np. Sorry, people always import as np. But if I do polyfit here, we can see this fits a least squared polynomial to the data we get, and we give it a degree, and our x and y points we want it to fit to. So once I do this, I should be getting like integers that follow this. The problem is, because this is instead an optimization problem, it ends up kind of giving a little bit funky values where it's not exactly the closest. Here you can see this actually gives us the polynomial we're looking for, or the coefficients of polynomial. But these are not actually round decimals. They're very, very close, but it just rounds it for us. So what I had to do to massage this is we do np.roundInt to round them to the closest integer, and then as type int to list. So now this is going to give us a list with our integers. So it's virtually going to look the same, but I do some things under the hood here that are important. Otherwise you end up with rounding errors. And then finally, we can go ahead and do sum poly I times target to the power of I for I in range 3. This is basically saying take my first coefficient, multiply it by target to the 0th power, which would be 1 in this case. Then take your second, I'm just going to run it again. Take your second thing, multiply it by target, so x in this case, or like for a polynomial x. And then take your third coefficient, multiply it by x squared. Cool. Alright, so now if I go ahead and finally run all of this, and I'll get rid of this print, I'm going to pray to God, and I forgot to use the submit flag, so we're just going to have to look by eyes. But here, if I copy this value, and then if I don't do it, you cannot be serious. Oh boy. Alright, but you're going to have to just trust me for this. You end up with the same value. I'll go ahead and let it run here, but you can click off the video by now. This is pretty much it. Yeah, I'm a little bit tired and my brain is not really working the greatest, but if anyone actually wants me to like go into depth and try to figure out why that property holds, I'll go through and do some reading. Just let me know with like a comment and like I'll try to get to it tomorrow. But yeah, so you can see here we get the right answer. This code is drastically slow, and the big reason why it's slow is all of this. If you actually go ahead and, like you saw with the earlier print statements, this part runs blazingly fast. NumPy is an insanely optimized language, and it's very, very useful used in the industry a ton. But this whole part is a pain because it ends up having to process basically like 3,000 something. It has to process this many points for each iteration near the end. And so it ends up being really slow. There's optimizations you can do. Like for example, you can collapse basically, like for example, if I'm solving the start point here and the start point here, it's the exact same calculation. It's just the grid is offset. So instead of just having p plus d, what I did was I also had like p plus d that was wrapped into the grid. And then I had basically the number, separate number saying which grid it was in. So this would be 0, this would be 1, this would be 1j, so forth. And that does speed it up. It just makes the code a little bit more complicated, so I didn't write it here. But yeah, if you're interested in seeing kind of that more optimized solution, I think I might have it on my GitHub, I might not. But yeah, other people have it better. So happy solving. Sorry about this day being ugly.